Thank you so much, Ashish, for that amazing introduction. I feel like I should stop now while I'm ahead, but I guess you're all expecting me to give a plenary talk, so I'll go ahead and do that. One of the things, maybe we can get the slides up. I'm not sure if there's something I need to do that, but there we go. So just one comment I want to say about the awards is that it's really true that for me, the mentoring and the education awards are the most important ones that I've ever received, because we all know as academics that it's really our students and our postdocs that are doing all the work. And you're also, as a mentor and an educator, kind of playing it forward. And so when I think about my impact on the field, it's really through the students and colleagues and people that I've mentored that I feel I've had the most impact. So those awards, I'm so glad that Ashu mentioned them, because often they're lost, or people think of these as kind of secondary awards, but for me, they really are the most meaningful. So with that, let me get started. So I've been working in wireless communication my whole career, going back to the mid-'80s. This is a super exciting time for wireless, and I hope in this talk just to convey to you a little bit about why I think it's such an exciting time, and what are some of the interesting areas for research going forward. But before I do that, I really want to thank ACM and SIG-Mobile for this award. I am truly speechless almost. I'm never speechless, but I'm almost speechless to be getting this incredible award from this community, particularly when I look at the previous winners. The prestige of an award is really about who wins it, and I feel very humbled to be in the company of some of the greatest pioneers in wireless communication, mobile networking, mobile computing that have won this award before I did, and the fact that they picked me to join this illustrious group is just really meaningful to me. So I want to thank, from the bottom of my heart, ACM, Ashley, for chairing this committee, SIG-Mobile for creating this award and for bestowing it on me. It really means a great deal. And this, by the way, is the first in-person conference I've attended since the pandemic began. And I'm delighted to be here, and to be here to not just attend the conference but accept this wonderful award is just something I'll always remember and treasure as my foray out of the pandemic and back to normal life. So thank you very much for making my first conference after the pandemic such a special one. And I'll just mention again, really this award is shared with my students and my collaborators. I've had the amazing good fortune to work with just an incredible group of people who inspire me every day, who challenge me, who are brilliant and creative, and so everything I've accomplished I really owe to the people that I've worked with. And by the way, Ashley didn't mention this, but I have not stopped doing research. That is my first love and my first passion, so I still have a research group. In fact, one of my dear collaborators from Princeton, Yasavan Gasampour, is here, and I am working on the second edition of the wireless book. So it's been a bit slow. Becoming dean kind of slowed that down, but I hope to finish it up soon, because the current version was written in 2005, so I already missed 4G altogether, and I hope I don't miss 5G before the second edition comes out. So with that, let me go to the topic, which is future wireless networks. And as I said, I've been working in this field. It's hard to believe, since the mid-'80s, but that's, decades of work in wireless communication. And I really do believe that now is the most exciting time of those decades for wireless. And the reason is that when I started in the mid-'80s working on defense communication with multiple antennas, cellular was just rolling out, analog cellular. I remember that McKinsey was a consultant to AT&T at the time, and AT&T said, should we move our researchers into wireless? And they said, no, there'll never be more than, 1,000 people that ever own a cell phone, because, it's too expensive and bulky, and, why do people want to carry their phone around with them? So obviously they were wrong, and pretty quickly in the late 80s, the move to digital cellular started heating up, and that's what actually inspired my PhD research. But we were really at that time only looking at how do we talk over the phone and maybe send, voice messages, talking to each other. As the 90s rolled out and Wi-Fi started in fits and starts becoming more prevalent, wireless was not just about talking to each other, but about accessing data from the internet or having our computers talk to each other. And then every generation since then of both cellular and Wi-Fi and other things like Bluetooth and Zigbee has really been about making those systems faster or more energy efficient. But now we're really seeing a paradigm shift where every device with an on-off switch is going to want to be connected to other devices and to the cloud for data processing. And that opens up a whole new set of challenges in terms of the type of communications that we need to support with our one wireless network, because we want the network to be seamless. So when I think about the applications, which are always what's exciting about wireless, even going back to the early days of the 80s to be, it's hard to believe now that the notion of talking on the phone where I could like walk around is such a bizarre concept, or travel, to another country and use my phone. This is now obviously something we all take for granted, but we're still not in an era where every device can communicate with each other. So that's what's really exciting. And it's not just for us geeks, the excitement of building the technology, but it's really the applications that this new wave of wireless is going to enable. So things like, of course, next generation and cellular, which we will continue to use to talk to each other and to send data and to watch cat videos on YouTube. But the next other sets of applications, I think, are what's most exciting in terms of what it enables, but also most challenging in terms of the technology. So things like smart spaces and smart cities. How do we make our cities more efficient? How do we enable self-driving cars and automation, not just for cars, but for trash collection and for fixing the broken lights and so forth? Enhanced reality, which is still something that we can't do over wireless because of the computational complexity, but, could I stand in my home in Princeton and actually really be here as a hologram talking to all of you? We don't have the technology to do that, not just the communication side of it, but the computation side, the small, low-cost devices and so forth. I think one of the most exciting areas for what wireless will enable is healthcare. I'm on the board of Medtronic, which is the largest medical device company in the world. And, Medtronic's mission is on a path to say we're going to eliminate drugs. Drugs are going to be barbaric. We're going to use electronics and signal processing and signal injection to cure pain, to cure incontinence, to cure Parkinson's and mental degenerative diseases. Maybe not cure them, but at least alleviate the constraints. And the tools that we have, it's not just for us researchers, it's not just about the wireless communication that we're going to enable, but our tools of communication theory and signal processing that's needed to create those biomedical devices that are going to transform medicine. We think about massive sensing. How can we use that? I mean, COVID is a great example. What if we could have used all of our cell phones to understand how the pandemic was evolving, or what risk you were at based on the people that you were around, or the place where you lived, or how the pandemic was surging in different parts of the country and different parts of the world? And there's things we can't even imagine. So when people ask me, what's the killer app for 6G? My answer is, well, 6G is really just 5G evolved a little bit. And if I knew the killer app for 6G, I wouldn't tell you I'd go start a company around it, although I think I'm too old to start a company at this point. But we don't know the killer app for 6G any more than Steve Jobs knew the killer app for apps, for Apple. He just built a platform where whatever the killer app was, or apps, or thousands of apps, they were enabled by the platform. And that's what we need to do with our wireless networks. So one of the big challenges is that there's not a lot of spectrum in the bands of the spectrum that's easy to use. So if we look at the licensed airwaves, so licensed meaning this is cellular bands, they were full as of 2014. Okay, so that's almost a decade ago, in that we had more data than we could support on the licensed band. So you might say, well, then how come I'm able to use my cell phone if the licensed bands have been full for a decade? It's really Wi-Fi. And Wi-Fi has a lot of spectrum, in fact, spectrum that's not fully utilized up in the 5 gig band. So when people say, oh, we have to go to mmWave or terahertz, we really don't yet, because we have a lot of spectrum in the Wi-Fi bands. It's just not fully utilized because of the challenges of propagation at those high frequencies. So when you say, okay, we're going to solve those problems by going to mmWave, well, you're introducing all kinds of other propagation challenges, many of which I think are going to be very hard to solve, at least in an ubiquitous way. We will have mmWave. I'm not sure about terahertz. We already have mmWave communication. Actually, we've had mmWave decades ago. There was a Wi-Fi standard in the 60 gig band that didn't do very well because doing propagation indoors at 60 gigahertz was challenging. So to say, okay, now we're going to do it outdoors, you can solve those challenges in the same way that multi-hop networks can solve the coverage problem, but you pay a huge price in performance and reliability. And so are we willing to pay that price? Not unless there's no other option. And so we really need to get to the point where we cannot support the applications we want without using mmWave for that to become ubiquitous. And then there's another really fun field that I worked in about 10 years ago. I was actually at Stanford since 1999, so 21 years at Stanford. I was like, oh, what happened to the 13 years? And I actually retired from Stanford, so this just goes to show you that you don't need to just play golf. When you retire, you could go be a dean or do other interesting things. But one of the things I did at Stanford before I left, which was really fun, and I think that there's interesting applications of it, is molecular communication. So there's going to be settings where you cannot communicate by electromagnetic waves, whether it's inside the body because it might cause damage to the organs, or within an oil pipe or under the ocean. And you can actually use molecules, acids and bases, to send ones and zeros. And so this was a super interesting area to work in, which is actually what got me into using machine learning for communication, which I'll talk about a little bit later. So there's all kinds of ways to get around the fact that the licensed airwaves are full, but these introduce completely different technical challenges, whether it's the physics of propagation at high frequencies, or in molecular communication, you're not communicating by electromagnetic waves, you're communicating by diffusion. So it's a completely different channel, it's a completely different mechanism of communication, which can be solved, but it opens up, kind of clean slate ways of doing design. Okay, so if the airways have been full for 10 decades, where the heck are we going to put all the Internet of Things devices in terms of what spectrum are they going to use? And this is an area, we've been talking about IoT for at least a decade, but it really is growing. It really is a reality today. There's companies that are making massive amounts of money on IoT. And the places where it's growing the most is in the connected home. So again, when we think about, okay, we have to build these wireless networks for, coverage outdoors, not necessarily, if a lot of the growth is indoors. But, it really spans so many different segments of commercialization. And that's what makes it interesting as a platform. How do we build a platform when some of these applications like connected cars, especially if you're doing visual recognition, or security where you're looking at video, you need really high bandwidth and really low latency. Whereas other things like, I need to send my vital statistics to my doctor every day, low data rate, low latency requirements. So how do we build one network that can do all of this? And I think that's one of the big challenges, going back to what I said earlier, which is that all of our wireless network advances have really been about increased capacity, increased data rates. We haven't focused on anything else. We're still not really very energy efficient. There was a lot of work on building low energy radios and low energy networks, especially in Europe, but we haven't really made much advances, at least not significant breakthroughs in those areas. We've still been focused on how do we get to higher data rates with our wireless systems. And that just needs to change, because the wave of Internet of Things isn't about how do we get higher data rates, at least not the segments that are growing the fastest. It's about these low data rate, low energy, something that can last on a battery for a decade. If you think about something you're implanting in your body to measure vital signs or to do deep brain stimulation, you don't want to go in and change the battery. I don't even like changing the battery on my fire alarms. Imagine having to change the battery on your, deep brain stimulation device. So we really need much better lower energy consumption wireless communication, but also the devices themselves. And the other thing that's been around for a long time as a challenge, but this community of wireless and networking, hasn't paid that much attention to it, is things like security and privacy and resilience. And now we're starting to see, if you're using these devices for automated cars or health, the notion of security and privacy is much, much, much more important than if you're watching cat videos on YouTube. So how do we embed these new networks that we're building to make them from day one secure, resilient, and private? And so I'll talk about that a little bit at the end. So I want to go back to the promise of 5G. 5G is here. This slide is about a decade old. It was a slide from when they were first conceiving of how do we sell 5G to get spectrum for it and for consumers and so forth. And so the idea was higher data rates. we want to get to more than 10 gigabit per second at peak, 10 years on a battery, and ultra reliable in terms of less than 1 millisecond latency. And do all this on the same network, although not necessarily for the same application or the same device. So what happened? How do we get all three of these simultaneously? Do we have that when you look at your phone or your watch today and it says you're on a 5G network? Are you able to do all that? Absolutely not. The only thing we really got to was high data rates. Like I said, that's what we know how to do, is make the data rates faster by going to higher bandwidth, but we certainly haven't gotten to 10 years on a battery. I mean, my smartphone dies every day, so if I forget to charge it, you know, I'm out of luck with my jogging counter. And we're certainly not at less than 1 millisecond, even on the backbone network, so it's not even necessarily the wireless network that's the challenge there. So why did we make these promises for 5G if we weren't able to keep them? I love this quote. So promises in pie crust are made to be broken, and that's especially true in wireless standards because that's the motivation for the next G. So how are we going to sell 6G communication? Well, we didn't quite get to the promises of 5G. So now we need more spectrum and more money to build 6G. And so right now we really are thinking about, you know, what should 6G look like? And it's going to look a lot like 5G in terms of the promises that we're making. So what are the enabling technologies to get us to whatever next G is, whether it's 6G or 7G or 8G? When people say to me, well, what is 6G? And I'm like, it's a marketing term so that Verizon can sell you a more expensive phone that has 6G on the terminal. But when we think about the evolution of wireless networking, which is a continuum, it doesn't, you know, go discretely with each generation that's called 5G or 6G or 7G. There's a lot of very interesting research that needs to get done to enable those promises that were made. So one is just rethinking cellular system design altogether. I'm going to ask a question because I like interactive. Talks. So my question is going to be when, and some people may know the answer, but anyway, my question is going to be, in what decade was cellular concept, this notion of putting base stations, breaking a regional area into cells, putting a base station in the middle, and having phones talk to the base station and then do handoff when they go between cells. So what decade was that done? So the first cellular phones rolled out in the mid-'80s. So how many people think it was the 80s when the first concept of cellular rolled out? Just raise your hand. 80s? Any takers for 80s? 70s? 60s? 50s? 40s? 30s? Okay, it was 1948, the same year that Shannon wrote his paper. There was a paper by D.H. Ring at Bell Labs who sketches out exactly this picture, not with the multiple antennas. There was only one antenna on the base station, and it was all analog, of course. But that was the concept. And we have not changed the basic concept of cellular since then, except to evolve the physical layer and some of the ways the base stations coordinate with each other. So maybe it's time to rethink these networks, but of course, that's challenging. Also, the backbone network. I mentioned the backbone network is the bottleneck when it comes to latency a lot of the time. Also, if we're looking at cloud communications, we need to think about the backbone much more than we've done in the past. So that's another interesting area, which I'll touch on a little bit later. Obviously, using more spectrum is important because if we're going to go to higher data rates, we need more spectrum. But also very low power radios, which again, we haven't made nearly as much progress. You know, people are building low power hardware, but has the communication theory evolved to look at low power? Has the networking protocols evolved to look at low power? They haven't. And so these are things that we need to look at. It's not just to say, let the hardware designers solve the energy problem. Massive MIMO is obviously another place, and I'll talk about this a little bit more. Problem with Massive MIMO is that it's expensive, and the propagation, you know, you see this beautiful pencil-thin beam when you know the channel perfectly and there's nothing that gets in the way of your beam, but that's not reality, and that's one of the big challenges of doing Massive MIMO, especially in mmWave. There's also, you know, new MAC and PHY techniques, multi-hop routing, which, as I mentioned earlier, can solve the coverage problem but leads to other performance issues. Edge computing and caching, which is going to be really important for low latency applications. And then this notion of cloud and fog optimization, which I'll touch on a little bit later, we're doing so much now in the cloud. So much of our communication is going to the cloud and extracting information or doing computation. So how do we do that effectively? It really changes the paradigm. I mean, all of our communications up until now has been essentially point to point. We haven't utilized a server in the cloud or computation in the cloud very much in our communications. That changes the direction of the data flow. It changes what we need in the cloud. It also changes what we need at the edge, because if we have to wait to send the computation to the cloud and back again, we're probably going to violate some of these latency issues. And then I mentioned security, privacy, and resilience. And then there's also machine learning, this new, shiny new tool. So where does machine learning come in? You could say, I mean, if you're a true, disciple of machine learning, you could say, well, we can all go home. We don't need to do any of this research because machine learning is going to solve everything for us. I don't believe that, of course. We need to keep our jobs and keep getting grants and stuff, so we have to argue for our domain knowledge being important, but it actually is important. So it's a bandwagon today. I mean, there is this notion that machine learning can solve everything, and the question is, do we jump on or do we run away? And I've generally been of the philosophy that when there's a bandwagon, you run the other direction, because there's thousands of people writing papers on that, and very few people writing papers on the thing that's not the shiny new thing. And by the way, my highest cited papers were like that. I said, I don't want to work in that area. When I looked at capacity of wireless channels, nobody was looking at sending digital data over wireless channels. We were all doing, analog voice. So usually I run away screaming from bandwagons. But actually, and this was because of that molecular communication problem that I was looking at, we didn't have a channel model for communicating over a molecular channel. So how do you equalize a channel if you don't have a channel model? We just threw machine learning at it and beat the existing techniques for equalization handily. And then I said, well, maybe we should look at this. And it turned out that it was that work that convinced me that, in fact, if you bring domain knowledge of optimal equalization through Viterbi, along with knowledge of machine learning, you can do much better than what's theoretically optimal when the theoretically optimal conditions don't take place. And I'll talk about that in a moment. So we determined that machine learning could beat theory in physical layer design, particularly in the equalizer, but also in decoding, joint source and channel coding, which doesn't have a good model because voice and text and video don't have good mathematical models. You can beat the best compression algorithms using machine learning when the thing that you're compressing doesn't have a good model. Obviously, if it's Lempel-Ziv applied to the optimal model for random data, then you can't beat that, but you can if the model's different. Another thing which we haven't worked on yet, but when I think about where machine learning can make a difference is, I did a lot of work, as many have, on cross-layer design back in the, my early days at Caltech. And cross-layer design has never been successful. So it's always been, cross-layer design means you forget about the layers of, you do the physical layer and then the network layer and then the application layer. Do it jointly. It's never been successful. But maybe that's because the complexity of optimizing across layers is too hard. Even if you just think about the resource allocation problem, back in second-generation wireless, when we were looking at frequency division multiplexing and trying to allocate frequencies to different cells, that's a graph coloring problem, which is NP hard, and we've never been able to solve it well. So maybe this is where we need machine learning, is places where we have problems that we know analytically are intractable, that we don't have good solutions. Maybe we should try machine learning and see if it gives us any insights or even just better solutions. The security, privacy, and resilience don't necessarily lend themselves to good analytical solutions, so maybe that's a place where we should look. And I already mentioned the cross-layer design. So the work that we've done is on using machine learning in the receiver of a traditional communication physical layer. So this picture, other than the last block, which is, let's see if is there a pointer on here? I'm afraid I'm going to mess things up. Let's see. There we go. Okay, so the only difference of this system versus you open a communication book from the 1960s is I have a machine learning in the receiver. Otherwise, this is exactly the same as any communication block diagram. So how does machine learning beat a traditional receiver? Say you put Viterbi detection, which is optimal for maximum likelihood detection. Or if it's a channel without memory, you just do symbol by symbol detection, and that's optimal. Well, what if you don't know the channel? You can't do Viterbi detection unless you have the probability of y given x. That's what goes into your Viterbi decoder. So if you don't know the channel, you don't have probability of y given x, you can't implement Viterbi. And if you have some error in your estimate of the channel, and you have an equalizer which is basically inverting the channel, you're actually going to introduce more errors through optimal detection than if you did something different. So this is what we learned from applying machine learning to this equalization problem, is that when you don't know the channel, so if you don't know h of f, and you just use data, you use training to develop the neural network for your receiver, you actually beat optimal Viterbi decoding because you don't have the channel parameters. Now, you can't beat Viterbi if you know the channel perfectly. By definition, it's theoretically optimal, right? So you can't beat theory in theory, but you can beat it in practice, which means you don't know the channel perfectly, or you have a complexity constraint. So Viterbi decoding, if you have a channel with a lot of memory, uses up a huge amount of resources. So if you have a complexity constraint, machine learning can also beat Viterbi decoding if you don't count the training, which is unfair, right? Because the training takes up a lot of computational resources. If the channel isn't changing, you only have to do it once. But we're wireless folks. The channel is always changing. So that's not going to be the case. All right. So, so just to give you a quick snapshot of what we did, and I'm not going to go into much of the technical details, but when we started down this path of looking at machine learning for receiver design, I said, well, we'll just use off-the-shelf machine learning techniques. We're not going to develop new machine learning techniques. But what we realized is that in doing optimal detection of a channel with memory, you need to look forward and backwards. That's exactly what the Viterbi decoder does. But there was no machine learning algorithm that had this kind of sliding window of looking at the data. So we actually developed a new machine learning technique, to my surprise, because there wasn't one off the shelf that did this sliding window. So again, I'm not going to go into the details. It's called the sliding bidirectional recurrent neural network is what we developed, and there's a picture of it. But the idea was in a uplink of a cellular system, and this was using mmWave because that's a sparse channel that's hard to measure, can we use this sliding bidirectional recurrent neural network to do equalization versus Viterbi, and how does it behave? So what we found is that you lose very little. Obviously, it can't beat Viterbi when Viterbi knows the channel perfectly and there's no computational complexity constraints. But we came very close with the bidirectional. So the blue here is at the bottom. That's Viterbi with optimal channel parameters. And the green is what we get with this sliding bidirectional recurrent neural network, just doing learning the channel via training. Now, if Viterbi cut, which is where you cut off the Viterbi decoder at some point because of a computational complexity constraint, does worse in some cases than the neural network. And the most interesting thing was that the neural network was very robust to not knowing the channel perfectly. So having a range of SNRs, training on one SNR, and then running it over a range of SNRs. So we did almost as well as if we trained perfectly. And that's because the neural network is not trying to invert the channel. It's not assuming that it knows the channel and therefore decoding based on a known channel. It's doing something different. We don't fully understand what it does. And that's one of the problems with neural networks is you can show that your algorithm works well, but can you show why it works well, or when it doesn't work well, or how much training you need to do to make it work well? These are all open questions for using machine learning in this context. And as I said, we showed that with perfect CSI, obviously you can't beat Viterbi, so again, that's the bottom blue curve. But once you introduce errors in the CSI of the Viterbi decoder, this neural network does better. Now, one of the most interesting things to me about this work, and this is my last slide on the machine learning, is that obviously training is a huge issue with machine learning, and we don't have good analysis on how much we need to train or when we know we can stop training. So we had a 7-layer neural network that was doing the equalization. Now, why is it that the 5th layer needs so much training here? And so the blue is when you train from scratch. You don't know anything. Yet when we used the same trained channel and then retrained, so we used the same parameters of channel 1 and then we retrained for channel 2, which was a completely different channel, we didn't need to train as much, so that's the orange. So the orange shows how much the training went down when we started not from scratch in the training, but from a different channel. And so when I look at this, I think, you know, there's some mega parameters of channels that are embedded. So once you train on one channel, those mega parameters are kind of embedded in those parameters. So when you retrain, you don't need to retrain as much. We don't understand what those mega parameters are. We don't understand why channel 5 needs so much training from scratch, but not otherwise. So these are interesting questions, I think, to think about as we're using machine learning for equalization. And the only other thing I'll mention is that, and this is where domain knowledge comes in, what I showed you before was training end-to-end from scratch. But we know what's optimal. We know the Viterbi decoder is optimal if we know the channel parameters. So why don't we just use machine learning to learn the parameters and then do a standard Viterbi decoder? And that's what we did here in ViterbiNet. And the training is much faster because you're only trying to learn the channel parameters as opposed to the whole end-to-end system. And the complexity was a lot less. So now I'm going to move to mmWave Massive MIMO. And as I mentioned before, you know, millimeter waves, we know, have large attenuation because attenuation is proportional to f squared, where f is the frequency. So you go up to these high frequencies, you get very large attenuation. And so we can get around that through Massive MIMO in a perfect world by, you know, having this very large antenna that points the beam directly at the receiver that you want to talk to, and then actually path loss is no longer proportional to f squared because you've changed the antenna pattern. The f squared is associated with an omnidirectional antenna. So when you go to these Massive MIMOs systems, path loss is no longer proportional to frequency. So in principle, you get, you know, very good closing of a link at these frequencies. The problem is if you have scattering, if something drives in front of your receiver, there goes your perfect pencil beam. And this is why, in practice, millimeter wave is not very successful. Because once you go into an actual environment, even if you have Massive MIMO, the ability to learn the channel perfectly to point directly at the receiver is challenging, especially for a large MIMO array. And then even once you have your perfect, you know, link closed, something drives by, or it starts raining, or the receiver moves, and then you have to start from scratch. So it's very difficult to get a robust millimeter wave link closed with Massive MIMO, and that's why it's not ubiquitous outdoors or even indoors. If you look at why the indoor Wi-Fi 60 gig standard failed miserably, despite great technology, it was just because the laws of physics trump great technology some of the time. I think it's going to be very challenging to see millimeter wave ubiquitous, which doesn't mean we don't need to develop the technologies for the places where it is going to work, because it gives us a huge amount of bandwidth. So how do we get around that? We did a little bit of work, this was a few years ago, from one of my last Stanford students on blind MIMO decoding. So if we could do decoding without actually knowing the channel, then we get around this problem of having to learn the channel. And the way we did it, now, this is a very hard problem because, so Y is the thing that you receive, the symbols you receive, A is the channel which you don't know, and X is what you sent. So how can you learn X when you only observe Y and you don't know either X or A, plus there's noise? So the way we did this is first you have to constrain the modulation. So we looked at only MPAM or BPSK, so you only really have one dimension in which you're modulating the data. We assume rich scattering and a fairly small MIMO system, because if it gets too big, the complexity is too big. And so the idea is that assume the fading is block fading, so the channel's constant for some block of time. We want to estimate the channel well enough to be able to recover X. And so one way to think about this, it's not a traditional receiver design. You're actually, so you receive X, and you want to apply an operation to X that rotates back to the constellation that you started with. And it turns out that doing this rotation is a non-convex optimization problem. And we know that, you know, non-convex optimization problems are hard to solve. You can use gradient descent, constrained, but it's slow. And so what we came up with, and again, this is where domain knowledge helps a lot, is we observed that the solution is typically on the vertex of the entire space of solutions. So if you just hop among the different vertices, you're likely to land on the right solution much faster than doing a full search. And so the vertex hopping, you see here, has a pretty high probability of success. So it's on the order of, 99% of the time for both gradient descent and vertex hopping. But the time is orders of magnitude faster with the vertex hopping versus the gradient descent. So again, this is just an example of new problems that are arising in these new settings for wireless communication, where you say, we don't know the channel anymore. We have too many parameters to estimate with Massive MIMO and mmWave. Things are changing too fast. How can we develop communication techniques that are robust, that converge with high probability, and that are fast? And so this also shows the performance of this technique, both in additive white Gaussian noise and in fading. So you see that the vertex hopping does well, although it levels off at certain high SNRs. Maximum likelihood does not converge. It's just too complex. And of course, zero forcing and gradient descent do very well, but they're very, very slow, as we saw in the previous slide. Okay, so let me come to rethinking cellular system design. Actually, could I trouble you to bring me my water? Thank you. So as I said, these systems were originally designed in the 1940s with the idea of, thank you so much, the idea that you put base stations in the middle of the cell and you have the cars talk to the base station that they're closest to, and you do handoff. Now, we've certainly evolved the technologies for cellular systems. The traditional design assumed interference limitation. How did we assign frequencies to the different cells? It was to minimize interference. Then we got to frequency reuse of one, where you're using the same frequencies in every cell. But we never got around the notion that these systems are interference limited, which is no longer true because of signal processing. The other interesting thing, as a Shannon theorist, is that we don't know the Shannon capacity of a cellular system unless all the base stations have full connectivity to each other and do full cooperation, in which case it's just a single cell with a bunch of distributed antennas. That's never going to be the case because of complexity. I mean, the base station here in Portland isn't going to talk to the base station in Stockholm and in Helsinki. So we're always going to have to split up the cellular system, and we don't know the capacity in the case where you have different cells or supercells that are interfering with each other. So we don't have Shannon capacity to rely on for the cellular system design. We can look at it for the link, we can look at it within a single cell, but we don't know from Shannon how to treat interference, because the interference channel has been an open problem in information theory for decades. So we've developed techniques to have better performance in cellular, from multiple antennas to using multi-user detection to get rid of interference, to having the base stations talk to each other, and using relays and small cells. And as soon as you introduce all that technology, especially cooperating base stations and small cells within a big cell, and distributed antennas, you have to ask the question of what is a cell? What's the definition of a cell with all of these advances? And how do we design a cellular system based on that definition? And that's what I think is an interesting area to look at with respect to rethinking cellular system design. And the other thing to think about is, okay, so how should the systems be designed? What's the most important question to ask when you're thinking about design? So if I ask you, any of you, okay, how should a cellular system be designed? What's the first question you should ask? Anybody? Yeah, what's your performance metric? What do you care about? What are the trade-offs? So do we only care about capacity, which is how we've been designing these systems all along, maximize the number of users and the data rates that they get? Or do we care about coverage? Or do we care about energy? We've never cared about those things in designing cellular systems. And I'll give you an example of that. My home near Stanford was right off Sand Hill Road. Most expensive real estate in the Bay Area, right, where all the VCs are, right? My cell call got dropped every time I drove up Sand Hill Road to get on 280, because there's trees and there's hills. They don't even have good coverage in the most expensive place, probably in the whole country, right? Because they never designed cellular systems for coverage. They designed them, actually, they didn't care about capacity or coverage or energy. They cared about revenue, right? That's what matters to the operators. But of course, they have to sell you their packages based on you can get 10 gigabits per second. So when we think about these next generations of wireless networks, we have to look at, what do we care about? How are we going to trade off? Engineering is all about trade-offs. How do we trade off capacity for energy consumption for coverage? And this will require much more sophisticated management of the network, including managing small cells and large cells in the cloud. And this was actually the basis of my second company, Plume, which started out looking at managing small cells in the cloud. Small cells weren't happening in 2010, 2011. They're still not happening in the way that we expected them to. So we pivoted to doing that for Wi-Fi. But we are starting to see small cells evolve right now and roll out. And so how do we manage all these small cells when we just put them up to get capacity gain? The macro cells are tuned when they're first deployed, and they never go back and retune them. It's really remarkable how unsophisticated the rollout of base stations, large and small, is. It's like the dark ages where you have typically a guy in a hard hat who goes, drives around the cell and tunes the parameters based on that. So we can put software in the cloud to do this network resource allocation, even though, again, it's a graph coloring problem. We don't know how to do it. The challenge is algorithmic complexity. So frequency allocation alone, saying which frequencies the base stations should utilize and the mobiles talking to those base stations should utilize, that's an NP hard problem. Just without MIMO or power control or anything else, once we introduced all this, it becomes an NP really hard problem. But fortunately, we have a lot of good optimization tools to solve those really hard optimization problems. I think what's most interesting here is the notion of what should be optimized in the cloud versus what should be optimized in the fog. Because things are happening very fast on a cellular network, so maybe frequency allocation needs to happen much faster than you can do through a cloud optimization. And also cloud optimization, optimizing frequency allocation over an entire cellular system is incredibly complex. Optimizing it over a small set of base stations that are in close proximity to each other is a much simpler problem. And I think ML can also play a role here because, as I said, we don't know optimally how to solve these problems. And then there's also caching and edge computing. So I'm just going to show you one result where we looked at optimizing things in the cloud, where you have this incredibly complex problem of optimizing frequency allocation across all base stations in a system, versus breaking it up into neighborhoods where you have some number of cells coordinating about the optimization, and then they just interfere with the other cells. And so this was for a set of 20, 10 virtual cells here with single user decoding, 20 with joint decoding, which is better. And what we found is that there's a 10x loss going from each base station optimizing on its own versus centrally for the joint decoding case, and about a 55% loss in the single user decoding case. These are huge gains. So when you look at this, you see that there's kind of, if you have a few neighborhoods, say 3 or 4, you get back, especially in the joint decoding case, a lot of that loss. So you don't need to do fully centralized. You can break the system up into a small number of neighborhoods and do the optimization that way. So this means that, okay, we can do that for cellular. Maybe we should do the same thing for Wi-Fi. I mean, when you're in an apartment building, and this is, again, what Plume does, every Wi-Fi access point interferes with every other one. You can buy an enterprise network, which is what businesses do, but that doesn't work when you're in a setting where you have different owners. Even in an office park, you have different businesses with different enterprise networks. So maybe we should put software in the cloud to optimize Wi-Fi, and then we can do it for all networks, for vehicular networks, millimeter wave networks, and so forth. And this gets to one of the interesting things that we're starting up at Princeton, is looking at kind of the convergence of the wireless network design, which we've been working on for a long time, the cloud, because if we're going to be doing this optimization in the cloud, and IoT is going to be using the cloud for computation, but also the edge, how does the wireless and the cloud and the edge interact? And the edge is part of the backbone network. So I think as a community, we need to start talking more with the people that are designing the cloud, designing the backbone network. I know Mobicom does that, but not as much as it should. And so I think we really need to forge these collaborations to understand how we bring these things together, because we don't know how to do it yet. And back to the question of, well, what are we designing for? What are the metrics that we care about in this convergence? We haven't defined that yet. It's critical for next-G applications in order to support the requirements of these systems. So I'm just briefly going to say with security, privacy, and resilience, again, this is something that we haven't built into our designs up until now. We've thought about link failures, but not malicious agents that are trying to jam us. Military communication did that. You know, I mean, if you go back when I was starting my career in the 80s, most of the papers were about jammers and malicious agents trying to break into your network or overhear, or eavesdroppers. But now you have malicious agents that if you have a consensus algorithm in a sensor network, you could have malicious agents come in and make the decision different from what it should be because they're spoofing an actual trusted node in the network. So I think there's a lot of really interesting work to be done here with wireless network designers collaborating with people that understand privacy and security and resilience. I'm going to skip this last one because I'm running out of time. So let me just say, challenges of disruption in next-gen networks is complexity. You can't just, you know, solve a Shannon capacity problem for a point-to-point network like I did when I was starting out, and, you know, then that has a huge impact. These networks are so complex, we have to distill them down into simple problems that we can get insight from, and that's much harder to do now given the complexity. There hasn't been significant research for a decade, investment by the government. That has changed. Okay, there is now a realization that the US is behind and Europe is behind China, and so there's a huge amount of investment going into wireless. It's a great decade for doing research in this area. Wireless is not perceived as a hot field. Machine learning is a hot field, but hopefully now with all this investment and all the exciting applications of 6G, that's changing. Standards can stifle innovation. Hardware and software of these networks is proprietary and closed. We have to open it up to enable innovation. And then we aren't talking to the people that are designing the backbone networks in the cloud and so forth. Killer app for 6G is connecting the next billion. I don't care what technology we develop. The most important thing is that people that are not connected get connected. And that's no more apparent that that's the case than the pandemic, where people that were not connected were really left out of everything, social, work, education, et cetera. So we can do that. It's just a matter of cost. We know how to bridge the digital divide using cellular systems where that makes sense, using satellite systems where it makes sense. It's really a question of cost, commitment, policy, and politics, which we can't necessarily solve in this room. But we can develop technologies that maybe make it lower cost or easier to use. So let me just summarize. Next wave in wireless is upon us. It's such an exciting time to be in this field. We need networks that will support higher rates, extreme energy efficiency, and low latency with robust security, privacy, and resilience. That can't be an afterthought. It has to be part of what we built. There's many challenges to creating the technical innovations and disruptions we need, and connecting the next billion is the killer app. So thank you so much again for this wonderful award and for the opportunity to address you. And I guess we have a few minutes for questions. I know I went a little bit over, but hopefully we can take some questions.